Welcome back to our IoT course. In today's lecture on security and privacy, we'll talk about attack vectors and give a number of examples. So, security is still one of the most urgent problems that needs to be solved for IoT systems. And unfortunately, it's not very common that IoT systems that are out there actually were designed with a thought on security. So this, as you maybe have heard before, leads to this famous sentence, the S in IoT stands for security. And of course, there is no S in IoT, as you can imagine. So we have a challenge. Security, as we've seen already, is difficult to implement due to limited computational sources, cost pressure, inexperienced developers that come from an application domain and not from system software or cryptography software, insufficient hardware protection in small microcontrollers, which are typically for the IoT, and also in applications and operating systems, we can find software deficiencies. And this results in a number of different attack types on IoT systems or using IoT systems. So one attack is eavesdropping. So somebody tries to listen into your communication. Another one is a privilege escalation attack. Somebody tries to access resources or software that this person is not allowed to. There's a brute force attack where you just try all the passwords that are possible, for example, and a denial of service attack, which is usually done by generating a large number of requests, for example, to systems. And if you have a large number of machines on the internet under your control, like a large number of IoT nodes, that makes it very easy to implement these denial of service attacks. So, to go into a bit more detail here, eavesdropping means that an attacker could monitor a targeted network and could try to steal personal data by exploiting some of the security loopholes in the system and also some of the weakly protected connections between IoT devices and the respective server that's sitting somewhere locally or in the cloud. Using a privilege escalation attack, you can obtain unauthorized access to privileges or elevated rights. So this can be done either by an external attacker that tries to exploit loopholes in your system, or also by a malicious insider. So if you have a multi-user Unix system, for example, a regular user could try to obtain super user rights by executing specially prepared binaries that try to exploit a security hole in the kernel. So threat actors in privilege escalation attacks exploit privilege escalation vulnerabilities, and these include unpatched bugs like buffer overflows, a misconfiguration of a system, or some developer forgot to implement adequate access controls. Now, a much more primitive approach to breaking IoT system security is a brute force attack. So this brute force attack works since very many IoT device users actually never bother to change passwords on their system, or if they do, they use easy to remember passwords. So I guess still the worldwide mostly used password is 123456, closely followed by the password, which consists of the letters of the word password. Well, these are very easy to guess, and you can find lists of commonly used passwords. And brute force attacker just tries these passwords one after the other until he or she succeeds. So very often you don't need to succeed for a specific device because there's so many devices out there. So if you spread your brute force attack wide enough, you will be able to gain a number of devices. And depending on what you intend to do with them, like starting a denial of service attack or something like this, you don't really care if you are actually breaking the security of one specific device, like a specific sensor, which you want to reconfigure to deliver incorrect data, but you just want to use their network connection and you don't care what system they're actually running as long as they have an internet connection. So brute force attackers can access the targeted IoT connections quickly. All your IoT devices are obviously on the internet, so you can't really avoid connection without, well, imp- uh, yeah, just in inflicting a lot of overhead. So the threat actors here try to guess passwords using dictionaries, common word combinations, or just a list of common passwords to penetrate IoT networks. And finally, this also enables denial of service attacks, which are very common as so-called distributed denial of service attacks or DDoS. So these use a large number of devices to overload the network connection of devices. That these might be IoT devices, but it could also be done the other way around. You could use a large number of IoT devices to deny service to, for example, a large internet provider. And we'll see an example for this in a bit. So one of the most famous examples of botnets where IoT devices were involved is the so-called Mirai botnet that was detected about 5 years ago. It's also called the DIN attack because it was used to attack the machines of a network provider called DIN. So IoT devices here were used as attack vector. And this is the largest recorded distributed denial of service attack that was ever found on Earth. And this was launched on the service provider DIM, and it was using an IoT botnet. So a botnet is just a collection of a number of devices that are no longer under the control of its original owner, but of some malicious person. And this malicious person coordinates all these bots. Well, bot comes from robot, obviously. So there's a way to remotely control them in order to execute targeted network attacks. And the Mirai botnet caused a huge portion of the internet to go down, and this included services like Twitter, The Guardian newspaper, Netflix, Reddit, and CNN News. And this was actually possible by a malware that was called Mirai, that's why we have the name. And as soon as a computer, so an IoT device, was infected with Mirai, it started to continuously search the internet for other vulnerable IoT devices and then use a list of known default usernames and passwords for this specific device to try to log into that device. And then it actually propagated the Mirai malware to this new device. So in addition to running a DDoS attack, it also worked as what we call an internet worm. So very many authors of malware actually don't want to be out in the open, but keep their work a secret, obviously. So what do we actually know about Mirai? So Mirai affected mostly Linux devices. So we thought Linux is said to be much more secure than Windows, right? So how could we affect Linux devices with malware? We'll see it in a bit. So Mirai is a specific malware targeting Linux devices because these are pretty common on a number of larger IoT devices, and it turned these Linux devices into remotely controlled bots that were used as part of this botnet for different large-scale attacks on the companies we've seen on the previous slide. And it primarily targeted consumer devices, including IP cameras, so surveillance cameras or something like that, that were connected over Wi-Fi or home routers. And these devices, as we said, continuously scan the internet for the IP addresses of Internet of Things devices. So this is sort of a brute force attack. So you start at address 1111 and go until the highest IPv4 address. That's an absolutely feasible approach for IPv4. For IPv6, it might be a bit more difficult because you have so many more addresses. Now Mirai tries to identify vulnerable IoT devices by trying to log in, and it uses a table of more than 60 common usernames and passwords. So some of these are factory defaults. So when you have an IoT device, very often all of these devices come with the identical password when delivered from the factory. And you are, as a user, are expected to change it. But very many users never do this because they might be overwhelmed by the complexity or they might be afraid to forget their newly sought out password. So Mirai then, when it actually succeeds in logging in, it infects the systems with a Mirai malware, and that's just a user mode program running on it. So there's no real security hole exploited in terms of what we think of buffer overflows or anything like that. And the interesting thing is, Mirai doesn't change the file system because there's so many Linux distributions out there. Very many have the file system in a read-only flash storage, so changing flash is difficult. But since very many of these devices are powered on once and only shut down very rarely, it just keeps all this in RAM. So all the malware is in RAM. So the easiest way to get rid of the Mirai malware is just to reboot your router or camera or whatever device was affected. But since there were so many of them out there, as long as you didn't change the affected default password, then you were guaranteed to be infected again in the next minute or so. Mirai also tries to keep its own control over a system, so it tries to identify competing malwares, other malware that has infected a device before, and removes it from memory and block remote administration ports so that nobody else can come in. And there were several DDoS attacks in addition to the ones we described before. So, for example, on the website of a well-known security researcher, Brian Krebs, with his Krebs and Security website, and this reached a total throughput of 620 gigabits per second. And there was another attack on a French web hoster called OVH reported, which is said to achieve 1 terabit per second throughput. So that's an amazing amount of data. And of course, if you have to pay for this data, then you might also have financial problems afterwards. So interestingly, the source code to Mirai was published, so you can find it on GitHub, and we've given a link here, of course, only for research purposes. And this includes such a list of passwords. Now they're encoded as hexadecimal numbers, so we give the ASCII representation on the right-hand side, and you see we have simple password pairs like root and user and admin and whatever you can imagine. So nothing that takes a lot of imagination to figure out. So the question is, which vendors were so stupid to choose simple default passwords and not force the user to change them at the very first startup of the device? Well, quite a number of them. So this is a list that might be incomplete. This was assembled by Brian Krebs, and you can easily find the list of usernames and passwords included in the source code. And there were several device types. I won't name any manufacturers here, obviously. So there were IP cameras that were affected, routers, but also printers, voice over IP phones, smart speakers, TV receivers, and digital video recorders. And these were many different manufacturers, and not only unknown, small, Far East manufacturers, as you would imagine, that operate under an extreme cost pressure, but also well-known names from the entertainment industry. Of course, it might be that these companies just bought the devices they sold from a small, not so well-known Far East company and just relabeled them. This would be one explanation, but I think that even in larger companies, the idea of really building secure devices hasn't really caught on. So the question is, how does this actually work? Because if you look at your home network, you know that your internet connection goes through a router. So this router has the only official IP address. So you're assigned this official IP address, usually dynamically, by the DHCP address assignment server of your internet provider. And this might be an IPv4 or an IPv6 address or both. All devices behind the router, so all of your private devices that you want to connect to the internet, might be over your home Wi-Fi. These don't have official IP addresses, so these have what we call private addresses. So some address ranges in IPv4 are reserved for exactly such purposes. And you've probably seen that before, so 192.168.xx is one of the address ranges, and another one is 10.xxx. So all addresses starting with 10 in the first byte, or all addresses starting with 129 in the first and 168 in the second byte, are non-routable private networks. And the question is, if they are non-routable, how can you actually connect from these systems to any server on the internet? You can usually not send a packet out, and you cannot receive a packet back, because the internet doesn't know how to route packets, intentionally doesn't know how to route packets from and to these private addresses. Now the trick here is to use what we call network address translation. So the router actually has a functionality to rewrite the source address of every packet that goes out from your local network into its own official address, and then sending this packet to its destination, possibly changing what we call the port number, which identifies the connection, because these port numbers might overlap between different devices you use at home, and then it keeps a table of the open net connections, so of the open TCP and UDP connections, for example, and whenever a packet comes back, then it does a translation in the reverse way by sending this packet to your local machine 192.168. Something something. So this network address translation takes place at the router, and usually it actually only allows to just run outgoing connections which receive replies. But of course, there are some devices which might also require some incoming connections. For example, so that an IoT device on your home network would be able to present a web administration interface to your mobile phone applications, which you can use anywhere on Earth on the internet to control whatever you're heating or your window blinds and so on. So there is a technology called Universal Plug and Play, UPnP, with which an IoT device or any device actually can request a router that does not to automatically open specific ports on the router side, so with the official IP address, and to forward anything that arrives at these ports to that specific IoT device. So essentially, we created a tunnel or wormhole through our nicely protected NAT network. And very often you don't know this. This is just a protocol going on between your device and your router. And if you don't disable it on the device and or on the router, well, it's just done without you even knowing. So this exposes TCP and UDP ports of vulnerable devices to attackers, which includes SSH ports for a remote terminal login, or even primitive telnet ports, which actually send passwords unencrypted. Some devices still use them, or a port for HTTP, HTTPS, which allows you to log in to your device using a web interface, given the credentials you have in your password file. So essentially, what did we learn from Mirai? Interestingly, Mirai did not rely on any specific known security deficiency of the Linux kernel or the Linux userland. So it just uses this knowledge about username password combinations that can be exploited because they're very common on internet devices, and then it just tries. It shoots wildly and it hits a large number of devices which did not have their password changed. So uh, the problem is that very many of these devices were no longer supported. So you were never able to get a software update. For example, some devices had hard-coded passwords that could not be changed. So we learned that you should never implement an IoT device that cannot have their software or firmware updated or their passwords changed. We also learned that users are lazy or just overwhelmed by the complexity of a device. So actually devices should force changing the default username and password for a device and make it mandatory before it actually enables the functionality of that device. Of course, for a small IoT sensor, that might be difficult because there is no such thing as a user interface for that thing. And very often devices then open their own Wi-Fi access point, which you have to connect to using a smartphone and then use a smartphone browser to change the password. And that already is quite a hassle. So many people just ignore it and continue using a default password. Obviously, when you have a list of passwords, this is based on the idea that very many passwords are used in many cases. So passwords for IoT devices should be unique per device and not per device type, but per manufactured device, especially when these devices are connected to the internet in a way that you can try to log into them. Of course, IoT devices should be connected to the internet in most cases. And it's also important to always patch IoT devices with the latest software and firmware updates to mitigate vulnerabilities. And obviously, you don't want to do this by hand. So if there's an automatic patching service, that would be nice. But you probably know this from your mobile phone. Devices can run for a long time. So such a security camera might run for 10 years or longer. And maybe after a couple of years, the manufacturer doesn't exist anymore, or there's new models, so the old models don't receive any software upgrades, neither for features nor for security. And that's the same what happens to most mobile phones after only very few years. This not only creates a lot of electronic waste, but in turn it creates a lot of dangerous situations because of security holes that are never going to be patched. So at least some device makers of the affected devices have learned. So as of 2016, some of the device makers of the affected devices have begun to require these unique passwords by default, and most actually have a minimum requirement on the entropy of the password. So they force a mix of upper and lowercase letters, numbers, special characters, and so on. But I'm not sure if this really helps because there's millions and millions new vulnerable devices where the developers still didn't take care of all these problems coming to the market every month. They will be connected to the internet and enable another attack vector. So I want to give you some other examples of IoT attacks, and this one here is outright scary. So this is a cardiac device, so essentially a pacemaker device that enables people with heart problems to live a relatively normal life. So this company that built these devices, which were implantable, built them so they had vulnerabilities that could allow a hacker to access a device. And there were not a small number of devices, but almost 500,000 of devices were affected. And once the hacker could actually access the device, they could do things like deplete the battery, so your pacemaker wouldn't work anymore, or even worse, administer incorrect pacing, so let your heart run really fast, or even electric shocks, which would be used usually to help in emergency situations but could kill a person. So these devices, like pacemakers and also defibrillators, are usually used to monitor and control the patient's heart functions and prevent heart attacks, but using this hack, you can actually exactly use them for the opposite function. This vulnerability occurred in a transmitter that reads the device's data and remotely shares it with physicians. So as we've seen, these devices are implanted, so plugging in a plug or a cable to connect to them would be really unpractical because you'd have to cut up the person wearing this device. So wireless is of course a very useful idea, but the problem here is, well, hackers could actually control the device by also accessing its transmitter. You had to be close, obviously, but very often you can be close to people wearing such a device. And if you're targeting a specific person, you know, this person takes the subway train every morning at 8, and you happen to stand next to this person in crowded subway and run the attack from a small embedded device in your pocket. Well, maybe you could kill that person or at least cause a lot of harm. And the firmware upgrade, as far as the internet says, was only provided by the manufacturer after 5 months. And still, this addressed only some but not all of the known cybersecurity problems of these devices. Even worse, this update is fast. It takes only 3 minutes in person with the patient's provider of the devices, but you cannot do it from home. So these devices have to be taken into a, well, service station, in this case, a physician, and then this software has to be updated. Now the problem is if I have an implanted device, usually when I update a device, it's non-functioning for quite a while and it has to reboot. So that might harm the patient, obviously. So at least one thing they had thought of is if there is some firmware update running and they provided for an option to do a firmware update, this device will run in automatic backup mode, a safe mode, which keeps all the life-sustaining features still available, but then still enables the firmware update to be performed. But still, I think that's scary. Now it gets even worse. So another medical device is a baby heart monitor. So this is a sensor that a baby can wear in a sock, and this monitors the heartbeat of the baby and relays data wirelessly to a nearby hub. So if you have a baby which unfortunately has heart problems, then you don't have to take care of that baby all the time, and sometimes you don't recognize the problems right away. So it's better to have a sensor supervising your kid. And this was tagged the worst IT security of 2016 by the British internet magazine The Register. Now, they figured out that by reading the end user license, you could have already expected something like this. Because if you read the end user license agreement that you have to sign to use it, well, clicking it somewhere on OK, so you agree to it. And this has a big section which indemnifies the producing company from litigation if the device malfunctions and the wearer of the device dies. That's not exactly what you expect from a medical device, isn't it? And the problem was that, well, the base stations itself were relatively secure. So they encrypted data sent and received from the manufacturer's servers, and the servers in turn contacted the phones of the parents if required. This again is a single point of failure, obviously, because if the servers fail or the cloud service is no longer available, then your device becomes useless, even though it's not really needed to use a server in any case. But what's worse is that the sensor itself was linked to a base station using Wi-Fi, and this connection is completely unencrypted and doesn't require any authentication to access. So you could access this Wi-Fi network of your baby monitor with any device that had Wi-Fi, and then you could send a single unauthenticated command over HTTP, and then you could force the base station to leave your home Wi-Fi network and join the one you've just created, for example, and this allowed you to take control of the system, monitor a stranger's baby, or prevent alerts from being sent out, whatever you can imagine. So pretty malicious things. So as you see, medical devices are more and more based on IoT technology, and we need to consider that these need to be protected much better than what's currently the case. Another example is not as critical, but still, yeah, terrifying. It's a webcam. So a webcam on the internet used for whatever, surveilling your home when you're not at home to see if there's no burglars and so on. So these things were actually called secure view. Well, what a joke. With various uses from home security to baby monitoring. And a hack allowed the attackers to view the video streams of the devices. And this was very simple. This was just unprotected information on the web server of the device. So if you accessed the URL HTTP IP of the device, then anony slash mjpeg.cgi, you could just watch the camera video stream without requiring any credentials. It's not clear if this was just left behind by accident or if this was a debug mode or whatever happened. But still, at least 9,500 cameras could be detected by security researchers found by a simple internet scan. And in the paper we linked, actually, they show a number of pictures they took from the respective video streams. In addition, the company producing these devices also transmitted user login credentials in clear, readable text over the internet for almost 2 years. So, and the mobile apps for the cameras also stored consumers' login information in clear, readable text on the mobile devices. So this is definitely not the way to do security, though it's probably not as critical for the life of a person as the other two examples we've seen before. Finally, we can, of course, also hack cars. So another example of attacks on IoT devices was done by researchers of the IBM Security Intelligence team, and they found out that you could easily hack a car by the company Jeep. And by doing this, you could take total control of this SUV using the so-called CAN bus. So the CAN bus is a bus system inside of a car that connects all the embedded control units of your car that control braking and windows and heating and whatever you can imagine that can be electronically controlled in a car. So you could exploit a firmware update vulnerability here, and by this you could hijack the vehicle over a cellular network which this car was connected to. And then the researcher could make the car speed up, slow down, and even steer off the road. So this can result in a serious accident, obviously. And the basic vulnerability was a wide open TCP port 6667, which provided the so-called D-bus protocol. This is a software-based event bus, which can connect to other bus systems and physical devices over the internet. So this led to a recall of 1.4 million cars that needed a software update. Well, the report is quite interesting to read. I'm not going into details here, but I think that's also scary because you would never think that a car could be remotely controlled that easily. So, what can we conclude? Security in IoT is a mess. IoT devices can be attacked, and you can compromise information on them or extract information, or you can also use them for network attacks like DDoS attacks. And here, IoT devices are especially attractive because there's so many of them out there. And the underlying security problems, as we've seen, are not always classical security holes, like an exploit for a buffer overflow in C code. Very often it's a sloppy configuration or badly written user-level code, and also, it's often what we call a layer 8 problem. So, layer 8 is the user, because the users are overwhelmed by the complexity. They want to use these nice new IoT technology devices, but they actually have no idea what's involved, what might be the consequences of using them. Uh, so, they don't, yeah, they want to do it with minimal efforts. They don't change passwords, they don't install firmware updates, and then yeah, they're really surprised if their devices are compromised. And some of the owners of devices infected by Mirror actually never noticed it because it was just running on a router. It, well, used a bit more of network bandwidth, so your home internet connection got slower. But still, well, that can happen due to many other reasons, so you probably didn't notice it. So, such a malware can actually hide for quite some time in the device, and very many malware writers also yeah, just have a malware infect devices, but then this malware lies dormant. It just checks using a communication channel, for example, over the IRC network, and then only when a special command to start, for example, a DOS attack is received by the bot software on the infected devices, then they would come into action. So they might be undetected for months or years even. So here, things need to be done. It's a sorry state the IoT is in, and I hope if you are going to develop IoT devices, you will take more care of that. So again, here's a number of references, and I think some of these, like the Mirai thing, the Mirai source code, and the Jeep case study, and the recording Black Hat paper are quite interesting to read. So thanks for listening, and until next time, bye.